Welcome to the very last lecture of this entire course. What I want to do today is simply conclude and basically talk a little bit about what are the highlights, meaning what are the main things for you to take with you when you leave this course. And the first thing I want to stress is, what did I aim, or what were my ambitions with this entire course? Well, my hope, first of all, was to basically talk about how to make robots move around in effective and safe ways using modern control theory. So, modern ways of thinking about systems and control signals and robotics. And as a corollary to that, I wanted to instill in you my strong feeling of that systematic and precise thinking and design is really key to making any kind of complicated system, like a robot, do anything useful. You can't just hack things together. You may get something small that works, but if you want to go big, you want to go complex, you want to go complicated, the hack won't cut it. Instead, you need to approach it in a systematic way, which led us to all of this wonderful theory about control systems in general and robotic systems in particular. But there's also this question of how do you actually go from the math to the robots. And another ambition I had with the course was, how do we actually bridge this theory-practice gap? My fourth and final, and maybe most important ambition, is for this course to have been amusing and intellectually stimulating, and most importantly, spark further investigations. I would be delighted if some of you, if all of you, went out and now started thinking about how do you make robotic systems do even more exciting and cool things than what we've seen in this course. So what I wanted to do now is just go through my view of what the punchlines are. Punchline number one is the model. We need a model of our system in order to be able to do anything with it, which means the model is important. The reason we need the model is the model actually gives us a way of predicting into the future what the system would do. Without that, we have no way of actually knowing what our controllers are going to actually make the system do. Now, the model is not the world. The model is an abstraction. Sometimes I even call the model a fable. Right? So what this means is that the model should be rich enough to be relevant, meaning it should have something to say about the real world, but it has to be simple enough to be useful. And in fact, I talked about this bananas versus non-bananas, non-linear versus linear systems. And the point is that in the universe, there are way more non-bananas than bananas. There are way more non-linear systems than linear systems, but yet the linear systems are rich enough to describe what's going on to a surprising degree of accuracy. Meaning, a lot of things in the world, even though they're not bananas, look surprisingly like bananas. Punchline number two. When we're designing controllers, feedback is the name of the game. Meaning, we're measuring what the system is doing, and we're using those measurements to influence our control decisions. Closing the loop is key. It's key for a number of reasons. One is that without feedback, you really have no way of knowing if what you're doing is any good. So if you want to do stability, for instance, and you don't have a perfect model, you need feedback. To track things, we need feedback. And also to build in some sense of robustness, feedback is wonderful, because our model is a fable, remember that. But the feedback mechanism kind of makes up for the fact that the model isn't perfect. And what we did is we talked about state feedback, meaning u is negative kx, or x hat, where hat is the estimate, and observers. This is the standard feedback model that I want you to take with you. Which brings me to one of my more humoristic jokes. So, ladies and gentlemen, did you hear about the feedback joke? No? No? Well, I guess that means you're out of the loop. Hilarious, right? Very good. Punchline number three, architectures. We cannot go directly for the full-blown dynamical robot system that just ain't going to work. So what we did is we had a 3 abstraction layer architecture. You can add more. But the point is that we're going to have some layer where we're generating intermediary waypoints. This would be the AI layer that we actually didn't talk too much about. And from then, we somehow need to turn that into reference trajectories, which I call the planning layer. And this is our wonderful hybrid navigation system, where we assumed, for instance, that x dot was equal to u. Well, this is going to give us desired directions to move in. And then the next layer is the tracking layer, where we make the robot actually follow the path that we planned in the planning layer. And we saw how to do this for a handful of different robots. Key among them was the differential drive robot, and that's the robot we also used in all our experiments. And this is really the way one typically thinks about, and should think about in my mind, how to decompose the navigation and control task for mobile robots. Punchline number 4. Whatever this dude from Georgia Tech sits here and talks at you about robotics, don't take my word for it. I would like you to go out, experiment, and tweak. And as you hopefully have seen, we have a simulator for MATLAB that is available as part of this course. Play around with it. Build robots. Make the robots do things. Tweak your algorithms. Make them better. And I want to actually stress this again. The field is not done yet. Remember the aliens that I showed in the last lecture? Well, there are lots of them out there. We don't know how to do everything in robotics. And that is another important punchline that I would like to leave you with. Which takes me to my final slide. I've really, really enjoyed myself, and I want to thank you for paying attention to it. I also need to thank some of the key players that have made this happen. You already have met JP, Jean-Pierre Delacroix. He has been the master of ceremony when we've done all the robotic experiments. The other key player is Amy Leviers, who you have seen dealing with a humanoid robot. You have also seen her providing glue lectures for coupling my lectures to the homework, and she has helped moderate things that have been going on in the class. I also want to point out Greg Droege, who came and talked to us about Segway robots. These are my 3 graduate students who have been instrumental in making this course what it is. I also want to thank Fatima Worth, who is an instructional designer here at Georgia Tech, who've helped me a lot with how do you actually think about putting this context together. And then we have the unsung hero of Brian Wilson, who has been patiently sitting behind the camera through all this, recording all my chit-chat. But finally, the person I really want to thank is not a single person, but all of you. I don't know what you look like. I don't know where you are. This is how I've been picturing you, or at least I would like to see you, woohoo, robotics. I hope you're not sleeping and bored. Instead, this is my view of you, and I hope that you have had a pleasant and intellectually stimulating experience throughout this course. Thank you.